Topic of my presentation is on conductometric method for the determination of corrosion of aluminium metal in hydrochloric acid medium.
Okay.
So slide is not moving.
So how can I say that? Yeah, now it's working.
Okay. We know aluminium and its alloys have widespread application in engineering technology due to their low cost, lightweight, and high thermal and electrical conductivities. The high corrosion resistance of aluminium is due to the formation of an oxide layer on the aluminium surface. The material's passivity can change with temperature or the previous passivation process of the metal. In acidic solution, the solution of aluminium at HCl is given below. There are several methods to protect aluminium and its alloy, among which anodizing process, conversion coatings, paints, organic coatings, and corrosion inhibitors are found to be more effective. Corrosion inhibitors modify the metal surface either by forming insoluble compounds with aluminium or by forming a protective surface layer. Most of the efficient acid inhibitor are organic compounds that mainly contain nitrogen, sulfur, or oxygen atom in its structure. Different types of compounds are used in corrosion inhibitors. Commonly used natural material are shown here. We can use a plant extract, carbohydrates, amino acids, biopolymers, biosurfactants, and drugs. Many research investigations have shown that using drugs to prevent corrosion is safe, economical, and has no impact on the environment. So in the present study, we use a telmisartan drug as corrosion inhibitor for aluminium in HCl medium. The structure of telmisartan drug is shown here. The chemical formula of telmisartan is C33H30N4O2. It is a white crystalline powder. The experimental methods includes metal substrate preparation, preparation of inhibitor, corrosion measurement studies. For the substrate preparation, we use aluminium coupons as substrate, and it is mechanically polished with 8 to 100 grades of emery paper and washed with the distilled water, then degreased with the acetone and kept in desiccator before use. We use 5 different types of concentration of the said telmisartan drug in using stock solution of 0.5 molar HCl solution. The corrosion studies were conducted using electrical conductance method, weight loss method, then UV visible spectra, open circuit potential measurement, and surface analysis. Using weight loss method, we can calculate corrosion rate and inhibition efficiency of the aluminium aluminium coupons in different concentration of the telmisartan drug. Next, result and discussion. First one in a conductance measurement study. Here the figure shows the variation of electrical conductivity of 0.5 molar HCl solution in presence and absence of corrosion inhibitor. Here, from this figure, we can clear that conductivity decreases by immersion time. Generally,
what are the best conditions for the inhibition?
The organic molecules should possess either double bond or heterogeneous atoms like sulfur, nitrogen, or oxygen atom. And these heterogeneous atoms must contain pi electrons so that these pi electrons can coordinate with the charged metal surface, or there is a electrostatic interaction between the adsorbed molecule and the metal surface.
Okay. I want to know from your result and discussion in which case you are able to achieve the best inhibition.
As the inhibitor concentration increases, this corrosion rate decreases and inhibition efficiency increases.
Up to?
Sorry, sir.
Up to how much ppm of inhibitor concentration?
As the concentration increases, we studied in this study up to 500 ppm.
You want to say you are having maximum inhibition at 500
Yes,
500
sir.
ppm.
Yes, sir.
Have you tried afterwards?
Yes, sir. I also tried, but as the concentration of the HCl medium increases, the inhibition and the corrosion rate increases. This drug is not much soluble in HCl medium.
Okay. So, what is the reason for this best condition that you are getting 500 ppm? Can you suggest the mechanism for that?
Sir, all these studies showed that this is the best optimal concentration for this maximum inhibition efficiency.
Are you audible?
Sorry, sir.
I am not able to get the answer.
Can I continue, sir?
Yeah, please.
Okay, sir. From this figure, we can clear that as the conductivity decreases by immersion time, this is because of in general case the conductivity. This is due to the decrease of dissolving ions of aluminium due to the absorption of inhibition organic compounds. So the number of Al3+ ions in solution decrease by increasing inhibitor concentration. In this present study, the large bulky groups present in the drug plays an important factor to effect on conductivity. Also, the hindrance factor of this group cause decreasing in mobility of the ions in solution, so conductivity also decreases. Next one, weight loss method or gravimetric method. Using weight loss method, here we find the effect of inhibitor concentration. What is the effect of inhibitor concentration and effect of temperature on corrosion rate? From the effect of inhibitor concentration study, we can here seen that the increase in the rate of corrosion with increase in temperature for both inhibited and uninhibited acid solution. Increasing in temperature accelerates both anodic and cathodic reaction that reduces dissolved oxygen in solution and also accelerates cathodic diffusion, consequently increasing the corrosion rate. But we can here seen that at all temperature, as the concentration of the inhibitor increases, corrosion rate decreases. The absorption force enhances with the rising concentration of the telmisartan drug, and which blocks the aluminium active surface reactive site. This may be the reason why there is an increase in corrosion rate. Sorry, the corrosion rate, decrease of corrosion rate. From this figure, we can clear that the percentage inhibition efficiency was found to increase with inhibitor concentration.
But time is over. We are not having much time. So please conclude.
Okay, sir. The conclusions: the drug telmisartan is an environmentally benign and good corrosion inhibitor for aluminium metal in acidic medium. Inhibition efficiency increases with increasing the concentration of drug. The changes in electrical conductivity of the solution provides qualitative information about the strength of corrosion as well as extent of corrosion behavior. The results obtained from electrical conductivity measurements revealed that telmisartan was an effective corrosion inhibitor in acidic medium. The inhibition efficiency increases with increase of temperature. The inhibitors have a tendency to be more strongly linked to the metal surface. They are predicted to participate in chemical adsorption on metal surface. Increase in the drug inhibitor concentration leads the open circuit potential to increase more positive value, indicating information of a good protective layer on the metal surface. AFM reveals the formation of a smooth uniform surface on aluminium in presence of drug, indicating telmisartan exhibit good inhibition performance. UV visible spectroscopy study also reveals that the formation of aluminium inhibitor complex, the inhibition efficiency trend of inhibitor obtained from gravimetric and electrochemical studies are in good agreement.
Thank you.
My name is Sumant Saurav, a pre-final year undergraduate from Department of Mechanical Engineering, NIT Calicut. Today's topic for my presentation is numerical modeling and simulation of phase change material melting. I have done this project paper under the guidance of my professor and guide, Dr. Jagdisha T. The outlines of the paper are objective, methodology, energy equations used in simulation. These simulations are done in ANSYS Fluent software. Results, conclusion, and references. Firstly, we start with introduction of phase change materials. Phase change materials are material which can change its state when either heat is supplied or extracted from them. They are basically used for latent heat energy storage. The objective of this paper is to demonstrate the melting simulation of phase change material in ANSYS Fluent and to analyze contours of velocity vectors, density vectors, temperature, and liquid fraction vectors. Methodology. We have chosen paraffin wax for analysis. Heat is supplied to it from left side. This arrows show the heat supplied. For the calculations, we have used 2500 watt per meter square heat, and all the remaining three sides are maintained at adiabatic conditions. Mass of appropriate size is generated. Energy equations used in simulation. These are the equations that we have used in simulation. Here H represents enthalpy, ρ denotes density, V signifies the fluid velocity, and F represents the source term. H is sensible enthalpy. Here beta denotes the liquid fraction and L is latent heat for PCM. L is 0 when material is solid and L at time when material liquid, beta equals to 1. Now we come to the results and outcomes that we get from this analysis. The basic results and outcomes of this analysis are contours of velocity vectors, that is how heat is flowing inside the PCM when it is going through phase change. Density contours, how density of PCM changes when it goes under the change of state. Temperature contours, how temperature changes with change in state. And liquid fraction contours at time, how much PCM is in liquid state and how much in solid state. First we start with velocity vector contours. Presence of red zone within the liquid PCM is situated near the left hot wall, exhibiting the highest magnitude of velocity. When all the PCM comes to liquid state, all the molecules within it comes to rest. Density contours. As the temperature within the PCM increases, the density of material decreases, leading it to rise, accumulate at the top, and ultimately form a region of low density PCM at the uppermost part of the domain. Low density region is represented by blue color here. Temperature contours. PCM begins to melt when the temperature at any location within it reaches 331 Kelvin. Development of red zone within the PCM. We can see that the red zone development within it starts at 90 minutes. This red zone is developed due to the interaction of the side of the PCM with the heated surface and the turbulence generated due to them. The red zone is generated on the left wall of the PCM due to its interaction with heated surface. Properties of all the materials almost constant when all the PCM is converted to liquid state. Our last result is liquid fraction contours. The rate of melting is constant in the initial stages, but as the time advances, rate of melting also increases. Melting of upper layer of PCM chambers takes approximately 60 minutes, while completing the melting in half of the PCM takes about 120 minutes. This observation contributes to the temporal and spatial dynamics involved at the melting process. We have represented graph shows the percentage of liquid fraction present at a certain time interval. The percentage of PCM transitioning from a solid to liquid state over time, initially at t equals to 0 minutes, all the PCM is in solid state, yielding a melting fraction 0. By the end of 240 minutes melting cycle, the entire PCM has completed the phase transition, resulting in a melting fraction of 100. Other key highlights of this graph are 19% liquid PCM at the end of 30 minutes, 47% at the end of 90 minutes, and 87% at the end of 210 minutes, and all are converted to liquid at the end of 240 minutes. The conclusions that we get out of this paper are: heat energy supplied from left wall, keeping all other sides at adiabatic conditions. Melting occurs at a relatively constant rate and consistent rate in the beginning, while rate of melting increases as time advances. In the initial phases, major heat transfer occurs through conduction, but as the time progresses, convection becomes significant. This is a major conclusion that we can draw here, as because in the beginning only solid phase is there, so conduction can take place. But as the time advances, some liquid fractions are also there, so convection also can take place. In the initial 30 minutes, conduction plays a dominant role, but as the heating progresses, a shift toward natural convection becomes significant. Care should be taken while selection of mesh size and time step error. In this, it can divert the results from the desired. The references are taken from below, maximum of which are journal papers on which phase change material simulation, renewable and sustainable energy reviews. Applied thermal energy journal papers are there. Thank you for giving your precious time on listening to my presentation.
Fine. Yeah, it's fine.
Yeah. So I was discussing about the introduction. So how is lithium-ion storage systems are very important. And we know that currently we use, especially in the market, what we use is liquid electrolytes. And liquid electrolytes definitely has safety concerns. So, so what we have tried to do is try to employ solid electrolytes, and especially our work was on the solid polymer electrolytes. And solid polymer electrolytes, when you compare with the liquid electrolytes safety issues are there, dendrite formation, other kind of thermal runaway, and all these problems are there. So if you use solid polymer electrolytes, all these problems we can overcome. And then these are highly flexible and can be processed into any of the form. So, but the problem with the solid polymer electrolyte is that the energy density what we get from a liquid electrolyte, we will not be able to get it through the using the polymer electrolytes. So what it's because the polymer electrolytes has a limitation because their conductivities are not very high. So what we can do is to improve the conductivity of solid polymer electrolytes. There are various methods that we can use, like you blend the polymer electrolyte systems with either with the nanofillers, or you fill it with the you mix it with different polymers, or you can just do with the plasticizers. So this is because the studies have revealed that the polymers, when it is in the amorphous phase, it is having a better conductivity when compared to polymers at the the normal one. So what we have to try to do is, what we have tried to do here is to improve the amorphous content of the polymer. So there are various polymers which we can use, like PVA, PEO, PVDF, PMMA, various polymers are there. But the majority of the studies are based on PEO, because PEO is semi-crystalline, high processability, and easily can make films. But the problem with PEO is that this is a semi-crystalline material. So you can improve the conductivity of the PEO using, as I said, we can use the fillers, or we can, those are the inert fillers, or we can use the plasticizers, or sometimes what we can do is we can blend the different polymers. So what we have tried to do is PMMA, which is a highly amorphous polymer. We have tried to mix a small amount of amorphous polymer like PMMA with PEO. So we have used two different kinds of PEO. One is the molecular weight 6, and the other one is molecular weight 10 to the power of 5. A very small fraction of PEO 5 and PMMA is used to blend with PEO. So every polymer has its own advantages and disadvantages. So what we have tried to do is try to tailor these, mix these polymer and tailor the system and get a better polymer electrolyte. So these were the solvents we have used, and the lithium perchlorate was used as a salt. So basic preparation technique was solution cast technique, where different polymers like PEO dissolves in acetonitrile, PMMA dissolves in acetone, mixing the two separately using a magnetic stirrer, and then mixing it together, keeping this stirring for about 48 hours so that you get a homogeneous viscous solution. And this homogeneous viscous solution, once it is formed, this is poured on a petri dish and allowed to dry under vacuum conditions. So it is kept in a vacuum oven. So once it is dried, the film is peeled out, and what we can see is the film which is formed, which is the complex film, or the film which is the blended film with the PEO and the PMMA. So that is what is a transparent film. So then once the film is formed, we will have to go for characterization. So there are various characterization techniques. We'll have to look into the structural characterization, and we also have to look into the electrical characterization of these systems. So the first thing what we have tried to do is to take the extra XRD of these samples. So what you can see is the first thing is the PO, pure PO, then the pure the perchlorate salt. We have used PO because it is easily solvable in this salt. And then we have pure PMMA. We can see that there's more of amorphous, whereas PO you can see that these are semi-crystalline peaks, where 19 degree and 23 degree are the characteristics peak of PO. And then when we mixed PO, two different PO with PMMA, which is this, you can see that how the peaks, so which is 19 degree, the peak at 19 degree and peak at 23 degree, how it is suppressed, the crystalline peaks are suppressed. And what we try to do is, we try to estimate the Scherer length of these peaks at these particular peaks, which is at 19 degree and 23 degree. And if you just look into PO, which is at 19 degree, so Scherer length is about 76.54 nanometer. And when you mix it with the polymers, different polymers, you can see that how this crystallite size is reduced. And in both the cases, whether you see whether the peak at 19 degree or the peak at 23 degree, in both the cases, there's a drastic reduction in the Scherer length of these systems. So, which means that when we are mixing with the different polymers like PMMA, we are actually reducing the crystalline behavior of the high molecular weight PO. And the next study, what we have done is with the FTIR studies. So FTIR studies were conducted on the systems with the pure system and with the mixed systems, that is the blended systems. So what we can see is in case of PO, where you can see some triplet peaks here, which is at 1060, 1093 and 1144, which is a semi-crystalline bands of PO. And there are other peaks which appearing at 839 and 1282, 1341 and 1413, which shows the CH2 rocking, twisting and wagging and scissoring of PO chains. So what happens basically when you take this polymer and blend it with either PMMA and then PO, the resultant is the top peak, which is for the mixed system, or it is the blended system, where you can see that the crystalline peak of PO, which was occurring at 1060 and 1144, is actually vanished. If you see those two peaks particularly, which means that the mixing of the small amount of polymers into these systems can suppress the crystallinity and we can improve the amorphous, which is also given by our XRD studies. And further, if you move towards the DSC, which is the thermal analysis of the polymer, we can see that the pure PO, the crystalline melting temperature of the pure PO is around 70.44, where this the enthalpy of heating. So for a pure PO, if I take it as 100% crystalline, if for a reference, this is taken for a reference, and then for the blend system, you can see that, and this is the inset of the figure. If you look into, you can see that how the melting temperature drastically reduces for a blend system, which is around 45.38. And if you take the percentage of crystallinity from a pure PO to the blend system, which is around 61.86. So further confirmation of our results, we have taken XRD, FTIR and DSC. In all the studies, we can see that we have actually suppressed the amorphous, the crystalline phase of the PO. So this is about the structural studies. So then we have to look into the electrical studies, because we are checking how better is our system and how better these systems can be used into the replacing the liquid electrolyte by a solid electrolyte. So what we have done is we have used an AC impedance technique using a CH instrument. This is a CH instrument which we have used. 608D is the instrument what we have used, and where we can get the complex spectra of the. So what we do is we varied the frequency from 0.1 to 10 to the power of 6 hertz, and then the response is taken. So this is the imaginary part, y-axis, and this is the real part. So where you can see two different kinds of a region. This is a high frequency region, and then you have the spike. Basically, for an ideal system, we get a semicircle, but as the conductivity of the system is improved, that semicircle will disappear, and then this region is what we are observing. So what we can see is for a complex system, we can see that you can see both for the inset of the figure is for a pure polymer, which is showing a higher bulk resistance. So the region on the higher frequency side, we call it as a bulk resistance, and region this spike, this is a low frequency region. So this is the bulk resistance, and this will give you the capacitance behavior of the system. Now, any electrical systems when you have such system which has showing these kind of impedance behavior, what we try to do is we use an electrical equivalent circuit to see how this electrical circuit is designed for these systems. So we have used an open source system, and we have analyzed this using the electrical equivalent circuit. So what you can see is an electrical equivalent circuit. So there are two, one is the line and the other one is the circle. So in this case, the circle indicates the experimental curve, and the line indicates a fitted parameter. So that is using this system. So what we can see is there is a complex phase element which is in series with the resistance. That is for the bulk property or the bulk resistance. And then you have another parameter which is in series with this, which is CPE2, which is called as a constant phase element. Basically, it is deviation from the ideal capacitance. And we can see the values here. For a pure system, around 19,000 ohms you can see. And whereas for a system which is blended with the polymer, the bulk resistance reduces drastically. And similarly, the complex impedance phase elements, we can see that even the constant phase elements also drastically reduced. So basically, our study was looking into the conductivity, improving the conductivity at lower temperature. So this is the conductivity at room temperature, which is showing for a pure system, which is around 10 to the power of -6, and for a system which is blended with the polymer, which is around 10 to the power of -4. So what we can see is we have increased a 2-order improvement in the conductivity when we have complexed with the, or when we mixed with the polymers. This is about the conductivity. Now, what is important whenever we design a polymer electrolyte or something, what is important is what are its transport parameters. So transport parameters will decide what is the conductivity of the system. So what are its basically transport parameters? Transport parameters are basically the diffusion coefficient, the number density, and mobility. So basically in a polymer, what happens is when the polymer chain is moving, the lithium ion will coordinate through the polymer chain. So segmental motion of the polymer chain is very, very important. So which will decide how will be the mobility of these ions moving in these systems. So now what we try to do is to look into the transport parameters and to check how these transport parameters are, whether these transport parameters have improved upon mixing with the polymers. So now we have used a method called as the BM method, which is Bandra-Melinda approach. Bandra-Melinda approach, using which what we try to do is from the complex spectra, we took the frequency and the tan phi, and the frequency peaks you can see. From the frequency peak, the relaxation time was estimated, and from the relaxation time, we estimated the diffusion coefficient, number density, and the mobility. And if you look into each of these parameters, you can see that how these parameters have improved upon addition of the polymers. So you can see that each of these parameters has improved at least a 2-fold or a 1-fold increase in the parameters, especially if you look into the number density, which is around 2-order change you can see, and then the diffusion coefficient 1-order change, and as well as the mobility, you can see that there's almost a 4-fold increase in the mobility of the system. So basically in a polymer, the lithium ion conduction takes place through the segmental motion, and to improve the segmental motion, the system needs to be in the amorphous phase. So what we try to do is to improve the amorphous content of the polymer and improve the conductivity of the polymer. So when the mobility increases, we know that the conductivity will also increase. So this is a different approach. There are different approaches. We have used this approach because this gives us a reasonably good result. So if you see the graph, we have both pure polymer as well as the polymer with the salt, and as well as the blended system, where you can see the circle as the experimental data and that is the fitted data. And we have used this formula to fit the equation, and using the fitting we could get the values, and we could see a large improvement in the each of the transport parameters, because any system or any polymer electrolyte.
Madam, can you conclude? Okay.
Yeah, yes, sir. I'm almost reaching. So therefore, finally, to conclude, we know that we have prepared polymer electrolyte with different blends. We could improve the conductivity, we could improve the amorphous nature, and various structural studies have revealed that there is definitely change in the amorphous content, and electrical studies are correlating with the structural studies. And these are the references. Thank you.
So my topic of presentation is a novel modification of activated charcoal sheet with polypyrrole and silver nanoparticles for removal of hexavalent chromium in water treatment processes. And this is the outline of my presentation, that is introduction, objectives and methodology, results and discussion, conclusions and references. So heavy metal poisoning is the biggest problem of today, and the heavy metals, they are cancerous, and due to industrialization and urbanization, the availability of fresh water, it becomes a very challenging issue. And hexavalent chromium is one of the main heavy metal pollutants, which is creating some problems. And there are very, you can say, many methods for removal of the heavy metals from aqueous medium, that is photocatalytic reduction, electrochemical treatment, adsorption. And adsorption is the most suitable method for removal of heavy metals from water. And in this study, our main objective is to develop efficient, low-cost, eco-friendly adsorbent material for removal of heavy metals from water. So the methodology used here is a two-step methodology in which activated charcoal sheet, they were used, and they were encapsulated with the silver nanoparticles and then capped with polypyrrole. And this is the schematic diagram. Then blend KC sheet, they were encapsulated with silver nanoparticles with silver nitrate and aqueous NaBH4 reduction method, in situ reduction method. And then the sheet HENP@AC so obtained was coated with polypyrrole by in situ suspension polymerization in presence of ferric chloride as an oxidant. And then we got the material. And then these sheets so prepared, they were used for reductive adsorption of chromium ions. That is, chromium 6 was reduced to chromium 3. And these are the HR FE7 images obtained for pristine AC sheet, then the PPY coated AC, and then AGNP coated AC, and then finally the PPY coated HENP encapsulated AC. And the globular structures can be seen in the figure D. And these are the EDS images obtained, in which the D part, it shows silver peaks, which were already absent in the EDS A diagram. And this is the quantification of the silver, in which the silver loading percentage is visible. And 0.1% silver was loaded. And this is the FTR spectrum, which clearly ensures the formation of polypyrrole and the encapsulation of AG nanoparticles onto the activated charcoal. And these are the XRT images, which shows the semi-crystalline nature of activated charcoal, and the HENPs also can be seen from the XRT pattern figure 4C. And the adsorption studies, these are carried in batch mode, and the adsorption efficiency and the one second. The adsorption efficiency and the QE, they were calculated using these formulas. And these are the effects on the adsorption, that is effect of pH, effect of contact time, initial chromium concentration, and adsorbed dose. And the pH was found to affect the adsorption process and the reduction process. And the optimum pH was reported as pH 2. And these are the comparison of the various adsorbents used, that is pristine AC and PPY at the rate EC and PPY AGNP spotted at the rate EC, the final material, and it was very efficient and recycling also done, in which the material was found promising results up to 5 cycles. And so, conclusion, the PPY AGNP AC CPN was prepared by in situ reduction method of aqueous agent 3 solution using aqueous NaPH4 solution to obtain AGNPs onto ACC. The subsequent capping of PPY onto AGNP at that AC. Excellent chromium adsorption efficiency of 99.8 and QE of 380 milligram per gram were displayed by PPY AGNP ACC in comparison to PPY AC and blank ACC. The encapsulation of AC with AGNP was found to improve chromium 6 and chromium 3 reduction process and improved adsorption capability. The PPY AGNP AC CPN sheet was reused up to 5 cycles in a row without suffering appreciable loss on
This is Dr. Suresh Kumar Jakka. I am from University of Aveiro, Portugal, and I'm working here for the past 10 years as a researcher. So let me introduce where is University of Aveiro, and it is in Portugal, which is the westmost country of Europe. And Aveiro is in the center of Portugal. Okay, Aveiro is in the center of Portugal. So it is like Venice of Portugal, where the seawater comes to the city, and it's very beautiful. So this is our university campus, and this is our administrative building. So our group activities, coming to our group activities, we prepare a lot of materials, ceramics, glasses, powders, crystals, etc. And we have a lot of facilities, and we do characterizations in dielectrical, magnetic, optical, etc. and many more also. And my interest is in optical materials, where we grow single crystals, glasses, and phosphor materials for luminescence applications. So we prepare materials through different methods like laser floating zone, laser surfaces, microwave, high temperature treatments, sol gel, auto combustion, either in wet or dry. So we have a lot of facilities. So these are basic facilities what we have for optical measurements. We have visible NIR spectrophlorometer, specs integrated with PMT photomultiplier tube. We can do experiments between 15 to 300 Kelvin and with a resolution of 0.01 nanometers also. And we have for NIR region, we have FTIR Bruker instrument, and we have Fluorolog VUV, vacuum ultraviolet spectrometer, which works in the range of 100 nanometers to 800 nanometers. We have home-built photoluminescence setup for temperature measurements. That means temperature-related photoluminescence measurements. And we have Raman spectrometer, which has like 4 sources. That is in the ultraviolet region, blue region, green and red region, and it has a resolution of around 4 centimeter inverse. So coming to the research topic, the emission of light or luminescence is a part of thermal radiation. The excess of light which is impinged on a substance can be radiated in the form of light as well. So according to the excitation mechanism, the luminescence can be divided into photoluminescence, chemiluminescence, thermoluminescence, electroluminescence, etc. And my interest here is on photoluminescence, which is broadly divided again into fluorescence and phosphorescence. So the luminescence, as I have told you, it is divided into many kinds of luminescence, where scintillation, X-ray luminescence, cathodoluminescence, photoluminescence, electroluminescence. These are different types of luminescence based on the excitation mechanisms, and these are used in different technologies. So, for example, high energy physics, PET detectors, X-ray amplifiers, CRTs, oscilloscopes, fluorescence lamps, LEDs, etc., etc. So here our interest is on photoluminescence, and the luminescence can be originated from different sources, like organic molecules also produce luminescence or photoluminescence, and small inorganic molecules can also produce photoluminescence. Inorganic crystals also can produce photoluminescence, and based on the characteristics of the materials and different methods used, they can be used in different ways. So, and how this photoluminescence is produced in the material. It can be from the host lattice or dopants or defects. So, some host lattices with their defects can produce photoluminescence, or explicitly dopants are extraordinary photoluminescent ions which produce light upon photon excitation. So the main ions which are responsible for photoluminescence in the transition metals are chromium, manganese, tin, lead, and in the rare earths it is europium, cerium, erbium, thulium, holmium, etc. So the luminescent materials, and they can also be classified into nanoparticles, microscale particles, large single crystals, ceramics, glasses, etc., where their importance of nanoscale particles is in molecular imaging, precursors, markers. Micro-sized particles are basically for lamps, LEDs, CRTs, PDPs, etc. Large single crystals in scintillators and lasers, ceramics in LEDs, scintillators and lasers as well, glasses in detectors and lasers. So the basic mechanism of photoluminescence is excitation and emission. There is an overlap of excitation and emission, but excitation and emission need not be of the same nature. So this is a schematic diagram of excitation and emission, where a host lattice is excited and emitted in the form of photons as well as phonons in the form of heat as well. So these are different representations of photoluminescence, where cross relaxations or configurational
second.
coordination diagrams like this. Yes?
You can skip to your work slides, sir, directly, no problem.
Yeah. Thank
Yes, sir, please, please. Okay.
So, so let me explain you this. The photoluminescence can be either from transition metals and rare earths. So the rare earths are having very cumbersome energy level. So there is a plenty of scope for the photoluminescence to occur from these ions as well. So the light is indispensable energy source for agricultural production as well, and the base. So some limitations are there based on season, changeable weather, different latitudes. So for the horticulture, the basic need is the absorption of light by cryptophrons, phototropins, and phytochromes. So these are the various absorption mechanisms of a plant, and a light source which is used in horticulture should have plenty of emission in these regions. So this is the absorption spectra, or photosynthetically active region, where the plant absorbs different wavelengths of visible light. So in order LED to be eligible for this plants to be absorbed, the light should be emitted in these regions. So there was a lot of research to attain emission in these regions. So this is the broad view of the work which was already done, and there are many materials which were developed to obtain emission in the region of red and far red region, like here. But there is no substantial emission between 600 to 750 continuously. And according to a company called Venazol Smart Light LED, the red and far red region LED is centered around 630, which is not ready to give all the emission, all the light which is needed for the plant to absorb in the red and far red region. For this, we have developed europium and manganese activated lanthanum aluminium phosphors, which emit in the red and far red region as a complementary to these LEDs. So we have synthesized lanthanum aluminum oxide doped with europium and manganese, where the XRD suits and exactly suits the diffraction pattern, and these are the SEM, where we got the particle size in around 1 micrometer. So coming to the excitation spectrum for lanthanum aluminum oxide, which is doped with single europium ion, we have a large spectrum with the excitation, which is attributed to the CTT, charge transfer transitions from oxygen to europium, and there are low excitation bands of europium. And this is the manganese excitation spectrum, where we have large band around the same region of CTT of oxygen in europium. So this is the emission spectrum of europium and manganese separately. That means single doped europium in LeVo and manganese in LeVo. So sorry, it is Mn4 plus. And the emission spectrum of europium is highly intense in the region between 600 and 750, and whereas the manganese, the emission is from 650 to 775 nanometers. So combining these two as a codependent, LeVo, europium and manganese, we have emission between 570 and 775, where there is a small gap here. So all this region is having emission from this lanthanum aluminum oxide doped with europium and manganese, co-doped with the europium and manganese. So the lifetime of these two, europium and manganese in LeVo, is almost the same, 2.84 and 3.16 milliseconds. And whereas if you see the PAR region of the plant in the red and far infrared region, so our material, which is lanthanum aluminum oxide doped with europium and manganese, is having emission from the region 570 and until 750. So there is a small gap here, which is covered by Vensol Smart Light. That means this LED can be accommodated with this phosphor, the developed phosphor, which is developed by us, LeVo, europium and manganese, and the total PAR region in this region from 570 to 750 can be, we can emit the light from 570 to 750 nanometers. So in that way, all the PAR region can be illuminated, and the plant can grow and absorb all the radiation in this region. So which is needed for the phytochrome and phytochrome PR and phytochrome PFR. So this is what we have achieved. That means this is an additional advantage of this material, which will compensate the region which is not illuminated by Vensol Smart Light. So this is also true for algae growth in the horticulture experiments. So in conclusion, we have developed a phosphor material which can complement the LED the commercially available LED. So thank you very much for your attention.